To start off the semester, I will cover the basics of units and dimensions. This topic is not terribly interesting, especially when compared to the content for the rest of the semester, but it is important and you must master it. Failure to get units correct can have dire and very significant consequences. Units are kind of like spelling, and that it's not interesting or fun, but you must study, learn, and master the subject, especially if you want to go on to become a professional in your career. And so I strongly encourage you to take this topic seriously. Let's talk about units and dimensions and the square bracket notation. Dimensions are classifications of different types of quantities, for example, mass, length, and time. Units are specifically how measurements in those different dimensions are measured. For example, inches, meters, miles, centimeters, and light years are all units of length. The square bracket notation is when we place square brackets around a symbol to indicate that symbol's units or dimensions, depending on the context. For example, if the lowercase letter m is a quantity of mass, then we could put the square brackets around m and say that that is equal to capital M, where capital M means mass. Or if we wanted to talk about its units, we could place the square brackets around m, and if m is measured in kilograms, we would say square brackets of m is kilograms. If t is a measurement of time, we'll use capital T to represent time. Or if t is measured in hours, we'll say that the units of t is hours. And then if x is a measurement of length, we can say that the dimensions of x equals capital L, meaning length. Or if x is measured in nanometers, we can say that the units of x equals nanometers. There are many systems of units, such as the metric system, SI, imperial, US customs, CGS, and others. In this class, we will primarily use the International System of Units. It is abbreviated as SI from the French translation. It was created in 1960 and was derived from the metric system. This is the most common system of units used all around the world and is especially used in education and science, even within the United States. This is an evolving standard and is periodically updated. It was updated in 2019 to adjust the definitions of kilogram, Kelvin, ampere, and mole to reference exactly defined physical constants. It is composed of 7 base units, powers of 10 prefix scalars, 22 derived units, and rules around formatting. We will cover each of those topics. There are some units that are not SI units, but are permitted to be used with the SI units. For example, minute, hour, year, degrees, liter, ton, electron volts, and others. Let's now review the SI basis units. The SI system is built on 7 bases, also known as coherent units. Each unit is defined in terms of a universal physical constant that is defined with an exact value. Below is the SI logo, which showcases those 7 units. The SI basis unit of mass is the kilogram, and it used to be defined in terms of the mass of a platinum artifact. In 2019, the definition of a kilogram was updated in terms of Planck's constant, which we will look at in a later chapter. The SI unit of length is the meter, and it is defined in terms of the speed of light. The SI unit of time is the second, and we will look at its definition on the next slide. The ampere, or amp for short, is the SI unit of electrical current, and it is defined in terms of the electron charge. Temperature has an SI unit called the Kelvin, and it is defined in terms of Boltzmann's constant, which is a parameter that converts temperature into thermal energy. The amount of substance is called the mole, and is defined in terms of Avogadro's number, which is the number of carbon-12 atoms needed to make 12 grams of carbon. The SI unit of luminous intensity is called a candela, and it is defined in terms of the intensity of a green light. SI units are often named after famous scientists, but are not proper nouns. The spelling and symbol are exactly as shown. For example, a meter is a lowercase upright letter M, not a capital M and not italicized. Let's now look at how the SI system defines the second and the meter. The cesium-133 atom has an outermost unpaired electron. Due to a magnetic interaction with the nucleus, the electron's ground state is split in two. If the atom absorbs a microwave with a frequency of exactly 9,192,631,770 cycles per second, it will move into the higher energy state. The second is therefore the amount of time it takes 9,192,631,770 cycles of this type of radiation to complete. The meter's definition comes from the definition of a second and the speed of light in a vacuum, which is given the symbol c. The speed of light is defined to be exactly 299,792,458 meters per second. You can allow a photon, which is a particle of light, to travel for exactly 1 second. Take the distance that it traveled in that time, and then divide it into 299,792,458 segments of equal length. One of those segments is a meter. Next are the SI prefixes. The SI units can be scaled by powers of 10. Positive scales increase the unit's magnitude, and negative scales shrink it. For example, a kilometer is 1,000 meters, and a microsecond is 1/1,000,000th of a second. Here is a table of the more commonly used SI prefixes. You should recognize some of them. First is pico, which is 1 part in a trillion. Then is nano, which is 1 part in a billion. Then is micro, which is 1 part in a million. Then is milli, which is 1 part in 1,000. Centi is 1 part in 100. Kilo is 1,000. Mega is 1,000,000. Giga is 1,000,000,000. And tera is 1,000,000,000,000. The correct symbol is exactly as shown. It is incorrect to change the symbol's case. For example, milli and mega are both M, but the case matters. SI prefixes only go with SI units. For example, a kilometer is okay, but a kilofoot is not. When combined with a unit, the prefix and unit are one word. For example, kilogram and not kilo space gram or kilo dash gram. Let's talk about the micro symbol. Some pieces of software do not allow for non-ASCII characters, or entering the Greek letter is cumbersome or inappropriate. For example, in a simple text file or in an email. So in those situations, it is okay to use the lowercase u symbol instead. However, in proper documents, you should go through the trouble to enter the micro symbol. Next, let's do an example problem involving the arithmetic with SI prefixes. SI prefixes are numbers, and so they obey the rules of arithmetic as any other number. As an exercise, replace the prefixes kilogram per cubic centimeter with their scalars and then reduce the unit. We'll start by writing kilogram per cubic centimeter and replace k with 10 to the power of 3 and c with 10 to the power of negative 2. In the denominator, we must be sure to put parentheses because the cubed operation goes to the c and to the m. 10 to the power of negative 2 cubed becomes 10 to the power of negative 6 in the denominator. A negative power in the denominator becomes a positive power in the numerator. So this now becomes 10 to the power of 3 plus 6 grams per cubic meter. 3 plus 6 is 9. 10 to the power of 9 is a billion, which in SI prefix is giga. So a kilogram per cubic centimeter is a gigagram per cubic meter. As an additional exercise, show that a kilogram per cubic centimeter is also equal to a gram per cubic millimeter. Next, let's review the dimensions of velocity, speed, acceleration, force, and see how derived units are found. Velocity. This is a quantity that is the rate and change of position. Speed is the magnitude of velocity and is the distance traveled divided by the time interval. So we can write the equation like this. Speed equals distance divided by time. To find the dimensions, we can apply the square bracket operator to every symbol. The dimensions of distance is length. The dimensions of time is time. And so therefore the dimensions of speed is length per time. We can then go ahead and rewrite the exponents as the dimensions of speed is length to the power of 1 times time to the power of negative 1. And there is no mass component, so it's mass to the power of 0. So then to find the SI basis units, we replace length with a meter, time with a second, and mass with a kilogram. So the SI basis units of speed are meters per second, or meters times second to the power of negative 1 times kilogram to the power of 0. Acceleration is the rate and change in velocity, and in the direction of travel is the change in speed divided by the time interval. We can write that in an equation like this. Acceleration equals change in speed divided by time, and then apply the square bracket operator. We know that the dimensions of speed are length per time, so then therefore the dimensions of acceleration will be the dimensions of speed with the time subtracted by 1 because we're dividing by time. So the dimensions of acceleration are length per time squared, or length to the power of 1 times time to the power of negative 2 times mass to the power of 0. Then, to find the SI basis units of acceleration, we replace length with meter, time with seconds, and mass with kilogram. So we get that the SI basis units of acceleration are meters per second squared. Force is the amount of strength needed to accelerate an object with mass, and its equation is force equals mass times acceleration. We can then apply the square bracket operator to this equation, and we get that the dimensions of force are the dimensions of mass multiplied by the dimensions of acceleration. So we can go to the dimensions of acceleration up above, and then increase the dimension mass component, increase it by 1. So we get that the dimensions of force is length to the power of 1 times time to the power of negative 2 times mass to the power of 1. And then to get the SI basis units, we replace length with meter, time with second, and mass with kilogram. And we get that the SI basis units of force are meter per second squared times kilogram. This combination of units occurs very frequently. We don't want to write it out all the time. So in honor of Sir Isaac Newton for his contribution to science, we call that collection of units the Newton, or capital N for short. So the derived unit of force is the Newton, and it's equal to a meter kilogram per second squared. As a matter of convenience, a derived unit is the name given to a specific combination of basis units that are multiplied and divided together. In total, there are 22 derived SI units, and a few of them are shown in the table below. The fourth column lists the basis units of the derived unit, and the last column shows how the derived unit can be expressed in other derived units. On the next slide, we will derive the joule and the watt. As an example problem, let's find the derived units of work and power. Work is the effort needed by a force to move an object a certain distance. The equation for work is work equals force times distance. We can then apply the square bracket operator to this equation and get that the dimensions of work equal the dimensions of force multiplied by the dimensions of distance. We know from the previous slide that the dimensions of force is length to the power of 1 times time to the power of -2 times mass to the power of 1. And the dimensions of distance is just length. So we can multiply those together, and we get that the dimensions of work equal the dimensions of length squared times time to the power of -2 times mass to the power of 1. Then, to get the SI basis units of work, we replace length with meter, time with second, and mass with kilogram. And we get that the SI basis units of work are meters squared per second squared times mass. In honor of Joule for his contribution to science, we call that combination of basis units the joule, or J for short. So a joule equals meters squared kilogram per second squared. Now we can find the SI basis units of power. Power is the rate at which work is done. The word rate always means per unit time, and so the rate at which work is done is going to be work divided by time. We can then take that equation and apply the square bracket operator, and we get that the dimensions of power equal the dimensions of work multiplied by the reciprocal of the dimensions of time. We can then plug everything in. We know from the previous problem that the dimensions of work is length squared, time to the power of -2 times mass, and then 1 over time will have dimensions of t to the power of -1. We then multiply this together, and we get that the dimensions of power are length squared, time -3 times mass. Then plug in the SI basis units. Length goes to meter, time goes to second, mass goes to kilogram, and we get that the SI basis units of power are meters squared kilogram per second cubed. In honor of Watt for his contribution to science, we call that combination of basis units the watt, or a capital W for short. So a watt equals meters cubed kilogram per second squared. We could, if we wanted to, say that, well, work is measured in joules, time is measured in seconds, and so therefore a watt is a joule per second. We could also recognize that a joule is a Newton meter, and so a watt is also equal to a Newton meter per second. Let's now review the rules for writing quantities with SI units. The unit symbol and prefix are case sensitive. So for example, a lowercase m, a lowercase s, lowercase kg, capital M followed by a lowercase m, and 2 lowercase letter m are all correct units. However, a capital M to be used as a meter is incorrect, or a capital SEC, a capital K followed by a lowercase g, or 2 capital M to represent millimeter are all incorrect units for the above quantities. Use only upright Roman characters that are not italicized. Multiplication of 2 units has a space or a dot between them. So for example, 24 Newton meters could be written in one of 2 ways. You could have a space between the Newton and the meter, or you could put a dot there. However, you should not have no symbol there. There should be a single space between the number and the unit symbol, no hyphen or underscore, and avoid line breaks. Here are 4 correct ways of writing a unit, and here are incorrect ways of doing it. In the first one, there is no space between the number and the unit. In the second one, the space has been replaced with a hyphen. And the third one, a space is placed in the incorrect location. And in the fourth one, the space has been replaced with an underscore. There isn't a dot at the end of a unit to represent an abbreviation, and a postfix S is not used to indicate plurality. So for example, with 50 kilograms, you should write it like that. You do not abbreviate kilogram as kg dot, and kilograms is not plural. You do not add an S at the end. Powers of units should be superscripted. So meters squared should be a lowercase m followed by a superscript 2. You should not write m and then the number 2 or m caret 2. Those two forms might be okay in an email or an Excel spreadsheet, but in proper writing, you should go through the trouble of finding the superscript. And writing an m space m is weird. People would be confused by what you meant by that, so definitely don't do that. Use only one division sign, and use parentheses as needed. So for example, 9.8 meters per second squared should be written like that. Sometimes you'll hear people say 9.8 meters per second, and that's weird, as the order of division is not very clear. It is better to say 9.8 meters per second squared. Or here's another example, 55.1 kilogram per meter second squared, not 55.1 kilogram per meter per second squared. It is not clear how the order of division goes, and so you should avoid that form. And then finally, compound prefixes are not allowed. The correct unit is 47 picofarads. It is not 47 microfarads. Please take a moment to study these, as you should use this style when writing in this class. On this slide, there are 40 quantities. Your task is to identify which ones have correct unit expression and which ones have an incorrect unit expression. If the unit expression is incorrect, identify why, and then make the correction. For the answers, see Appendix 1. Let's now review quantities that have a value of 0 and temperatures. For most quantities, a value of 0 is the same for any unit. For example, 0 meters equals 0 miles, equals 0 kilometers, equals 0 feet, equals 0 inches, equals 0 light years. And another example, 0 meters per second equals 0 miles per hour, equals 0 kilometers per hour, equals 0 meters per microsecond, equals 0 inches per minute. For these types of quantities, it is common to just say that the value is 0 and omit the unit. There are exceptions, most notably temperature and logarithmic quantities. For these quantities, the unit must always be specified. For example, 0 degrees Fahrenheit is not equal to 0 degrees Celsius, and both are not equal to 0 Kelvin. And additionally, 0 decibels does not equal 0 dBm, and both are not equal to 0 dB micro. The degree sign and space are required for Fahrenheit and Celsius quantities. The degree sign does not go with Kelvin, although it did in the past. When spelling it out in writing, the correct style is degrees Celsius and degrees Fahrenheit, as shown on the screen. For completeness, here is a short list of some Imperial and U.S. Customs units. These types of units originate from the English Empire and are still used in some limited capacity within English-speaking countries, most notably the United States. These units have a long and complicated history, and so the exact definitions of these quantities varies over geography and time. For example, a US and imperial gallon are different by more than 10%. These units, as you can see, are all over the place, and they do not form a well-defined unit system like the SI system does. The SI system builds on basis units which are defined based on universal physical constants, whereas these English units have nothing similar to that feature. And in fact, to help standardize these units, many of them are defined in terms of SI units. For example, 1 inch is exactly 25.4 millimeters. Although these systems lack the elegance and beauty of the SI system, they do work well enough for everyday people and activities. Let's now review the process of converting units. First, identify an equivalence relationship between your unit and the target unit. It will often look something like this, where A, measured in unit 1, is equal to B, measured in unit 2, where A and B are positive numbers. Step 2. Divide both sides of this equation by the side that has the unit that you want to convert away from. If that is unit 2, this is what it looks like. A, measured in unit 1, divided by B, measured in unit 2, is equal to 1. And finally, keeping units in your work, multiply your value C, measured in unit 2, by that form of 1. So you would say C measured in unit 2 equals C measured in unit 2 times 1, which is equal to C measured in unit 2 multiplied by A in unit 1 divided by B in unit 2. You can see that unit 2 will cancel out, and you are left with CA divided by B, and unit 1 is left over. Let's now do a couple of simple unit conversion examples. First, convert 88.3 inches to millimeters. First, you would have to look up that 1 inch is equal to 25.4 millimeters. You would have to then identify that the source unit is inches and your target unit is millimeters. So then take that equivalence relationship and divide both sides by 1 inch. So you get that 1 is equal to 25.4 millimeters divided by 1 inch. And then finally, do the multiplication. So 88.3 inches equals 88.3 inches divided by 1 times 1. And replace 1, we get 88.3 inch divided by 1 times 25.4 millimeters divided by 1 inch. 1 inch will cancel in the numerator and denominator, and we can do the multiplication, and we get that this is equal to 2,242.82 millimeters. The second example, convert 1,570 calories to joules and then kilojoules. So first we have to look up the equivalence relationship. That is that 1 calorie is equal to 4.184 joules. We then identify that the source unit is calories and the target unit is joules. We can then take the equivalence relationship and divide both sides by 1 calorie. And we get that 1 is equal to 4.184 joules divided by 1 calorie. And then 1,570 calories is equal to 1,570 calories divided by 1 times 1. Replace the definition of 1 in step 3 above, and we get 1,570 calories divided by 1 times 4.184 joules divided by 1 calorie. You can see that the calories cancel out, joules are left over, and after the multiplication we get that this is equal to 6,568.88 joules. We can then convert this to kilojoules by dividing by 1,000. And we get that this is equal to approximately 6.6 kilojoules. Let's now do a more complicated example where many unit conversions occur. Sometimes it will be the case that you do not have the equivalence relationship between your source unit and the target unit. In these scenarios, you will have several unit conversions. Here's an example of converting 1 mile to millimeters. First, you must know or look up the equivalence relationships. That is, 1 mile equals 1,760 yards. 1 yard is equal to 3 feet. 1 foot is equal to 12 inches. 1 inch is equal to 2.54 centimeters. And 1 centimeter is equal to 10 millimeters. Then you put it all together. And it looks like this. So 1 mile equals 1 mile divided by 1 times 1,760 yards divided by 1 mile times 3 feet divided by 1 yard times 12 inches divided by 1 foot times 2.54 centimeters divided by 1 inch times 10 millimeters divided by 1 centimeter. You can see that each pair of multiplication will cancel out the unit. So for the first pair, miles is canceled out. In the second pair, yards are canceled out. In the third pair, feet are canceled out. And then inches, and then centimeters, and millimeters are left over. After all of the multiplication, 1.61 million millimeters is the result. Let's do a compound example of converting flow rate. Convert 50 US gallons per hour to liters per minute. First, we'll identify the equivalent relationships that are needed. We know that 1 US gallon is equal to 231 cubic inches. 1 inch is equal to 2.54 centimeters. 1 cubic centimeter is equal to 1 milliliter. 1,000 milliliters equals 1 liter. And 1 hour equals 60 minutes. Then we put everything together, and it looks like this. So first, the first pair of multiplication converts gallons to cubic inches, and then cubic inches are converted to cubic centimeters. Notice that this third multiplication is cubed because we need cubic centimeters. And then cubic centimeters to milliliters, and then we notice that 1,000 milliliters equals 1 liter. The last term converts hours to minutes. When all the multiplication is done, we get 3.155 liters per minute. When reviewing this, you should notice that each pair, the units will cancel out. So in the first pair, gallons cancel out. In the second pair, cubic inches cancel out. In the third pair, cubic centimeters cancel out. In the fourth pair, milliliters cancel, and then liters are left over. And then the first factor and the last factor convert hours to minutes. Let's now review the different types of angular units. Here are their values for a full turn and a right angle. There's a full revolution, which for a right angle is a quarter turn or a quarter revolution. Then there are degrees, which is what you are probably most familiar with, where 360 degrees is a full turn and 90 degrees is a right angle. In radians, a full turn is 2 pi radians, and a right angle is half of pi. You might also have seen gradients, where instead of 90 degrees is a right angle, 100 gradients is a right angle, which means that 400 gradients is a full turn. Each of these different units is used in a different industry. Revolutions are often used for screws and machines with a spinning part, for example, a crankshaft of a motor. Degrees are used by engineers and anybody who is building stuff. And then radians are used by mathematicians and physicists. And gradients are used in anything that's related to the surface of the earth, so geology and surveying. And gradients are also abbreviated as G or gon, which comes from the Greek word, or given a percent sign. Here are the sign conventions. Positive angles are usually used to indicate counterclockwise rotation, and negative angles are used to represent clockwise rotation. Radians are the derived SI unit of angle. Well, you can see that the R, where R is the radius of a circle, and s is the arc length of a circle, and theta is the angle extended by that arc length. The relationship between those three variables is that s is equal to r times theta, and s is equal to r when theta equals 1 radian. So that is the definition of a radian. If the arc length becomes the full circle, we call it the circumference, and the angle is 2 pi radians. And this gives us the equation that the circumference equals 2 pi r, and 2r is equal to the diameter, so the circumference is equal to pi times the diameter. We can do a dimensional analysis of this equation. So we apply the square bracket operator to the equation, and we get that the dimensions of theta equal the dimensions of the arc length divided by the dimensions of the radius. And we get that the dimensions of the angle are length per length, which reduces down to 1. And so we can say that theta is dimensionless. We can then plug in the SI units, and we get that radians has units of meters per meter. Because of that, we often will omit the radian word. However, the other angular units are never omitted. As a matter of notation, there is no space between the value and the degree sign, so it is written 45 degrees, not 45 space degree. In some context, for example emails, it is easier to abbreviate or just spell out the word degree, so 45 degree would become 45 and then write the word degree. Let's now do an example problem of converting different angular units. Most treadmills can incline to a maximum of 15%. What is this angle in gradians, revolutions, degrees, and radians? As we saw in the previous slide, sometimes the percent sign is used to represent gradients. So 15% incline equals 15 gradians. We can convert this to revolutions, although I will tell you this would be an odd thing to do for this particular application, but if you wanted to, you could. You notice that 1 revolution equals 400 gradians, and so 15% incline equals 15 gradians times 1 revolution divided by 400 gradians, which equals 0.0375 revolutions. You can convert gradients to degrees. You recognize that a full turn is 360 degrees, which is also equal to 400 gradians. So 15% incline equals 15 gradians times 360 degrees divided by 400 gradians, which is equal to 13.5 degrees. And then finally, you can convert percent to radians. You notice that 2 pi radians is equal to 400 gradians. And so 15% incline equals 15 gradians times 2 pi radians divided by 400 gradians. After you perform the computation, you get that 15% incline is approximately 236 milliradians. The next topic is finding the dimensions of an unknown parameter. There may be a time when you are unfamiliar with an equation, but you can still identify the dimensions of a variable from the rest of the equation. Here are the rules. First, apply the square bracket operator to the equation or expression, and then solve for the unknown parameter using algebra and arithmetic. Each addition and subtraction term must have the same dimensions. So, for example, a plus b, if a is a measurement of length, then therefore b must also be a measurement of length. It would be illegal to, for example, add 5 seconds and 2 meters. Both sides of the equal sign or a comparison operator must have the same dimensions. Special functions such as trigonometric, logarithmic, and exponential functions all have dimensionless arguments and then return to you a dimensionless value. So, for example, log of 2 kilograms is illegal. And then finally, if a variable is dimensionless, then when you apply the square brackets to it, you say that its dimensions is 1. Let's do a dimensional analysis example problem. In this problem, find the dimensions of all the Greek letters in the following equation. T times alpha divided by the quantity beta plus m is equal to r times cosine of omega t minus phi. Where capital and lowercase t are measurements of time, m is a measurement of mass, and r is a measurement of length. First, we'll start by applying the square bracket operator to the entire equation, and this is what we get. The dimensions of t times the dimensions of alpha divided by the dimensions of beta plus m equals the dimensions of r multiplied by the dimensions of the cosine function. There is an addition on the left-hand side's denominator. Those two terms must have the same dimensions. These are beta and m, so the dimensions of beta equal the dimensions of m, which is equal to mass. On the right-hand side, the cosine function returns a dimensionless value, so the dimensions of the entire cosine function equals 1. We can then insert what we know, and we get that time multiplied by the dimensions of alpha divided by mass equals length times 1. Then solve for the dimensions of alpha, and we get that the dimensions of alpha equal length times mass divided by time. The argument of the cosine function is dimensionless, so we therefore say the dimensions of omega t minus phi equals 1. The two subtracted terms must have the same dimensions. So the dimensions of omega t equal the dimensions of phi, and these are on the left-hand side of the equation sign, and so they are both dimensionless, so we'd say it's equal to 1. We can then distribute the square bracket operator on omega t, and we get that the dimensions of omega times the dimensions of t, which is equal to the dimensions of omega times time, is equal to 1. Then we solve for the dimensions of omega, and we get that the dimensions of omega equals 1 over time. We can summarize everything that we found. The dimensions of alpha equal length times mass divided by time. The dimensions of beta equal mass. The dimensions of omega equal 1 divided by time, and phi is dimensionless. Let's now talk about where and how units are labeled. So the main question is, where do units go? And the short answer is they go everywhere. If you have a chart or a plot, you need to include units on the axis labels. If you have a data table, you need to include units in the data table or in a header row. If you have a spreadsheet, you need to indicate the units where appropriate. In writing in sentences, you need to include units. If you're showing computations, you need to include units in your work. And even if you're speaking, you need to say the units that you're using. Let's talk about how units are indicated. Before I get into it, I want to mention that in specialized pieces of scientific and engineering software, it will have very specific requirements for how to enter and display units. And you must review that program's documentation to learn what it requires. But in writing, you need to indicate a value, a space, and then the unit, and use proper capitalization. Remember, units are not proper nouns. Don't use italics. You may spell out the unit. The SI unit and prefix are one word. Some writing styles require a hyphen in certain situations. And that's another thing to note. In writing, certain rules vary, and you must refer to your appropriate style guidelines for how to use units in that context. For charts and plots, write the unit in parentheses after the label. Some sources will divide the label by the unit instead. For data tables, write the unit in parentheses at the top header row, unless the units vary from row to row, in which case the unit must be indicated in each row. In this case, you may include a dedicated column for each row's unit. For spreadsheets, either include the unit in a dedicated cell adjacent to the value, include the unit in a label cell, or create a custom cell format to display the unit. In speaking, just say the unit's name and the value like you would any other word, and use the correct plurality. We'll look at examples of these on the next slide. Let's now do an example problem of including units in a sentence. Identify each of the options on the right as either correct or incorrect to fill in the blank in the two sentences below. The first one is a sentence that reads, I gave Caleb a blank battery to power the flashlight. And the second one is a question that reads, what is the battery's voltage? Fill in the blank. Let's go ahead and look at each of these 9 options. Option A is 9 followed by a lowercase letter v. This is wrong, as the correct symbol for voltage is a capital letter V. Option B is just the number 9. This is wrong because the author made no attempt to include the units. Option C is almost correct, but the author needs to include a space because 9 and volt are 2 different words. And D is correct, 9, a space, and then a capital letter V. Option E would be okay in certain types of circumstances, but in proper writing, for numbers less than 10, you should spell out the word 9, which is the case in F. And because 9 volt is an adjective that describes battery, you should hyphenate it. And that is why G is wrong. In H, volt is treated as a proper noun, and so that is incorrect. And that is also the same case in option I. Volt is not a proper noun. This leads us to the question, well, which of those 2 options is best for each of those scenarios? Well, the first scenario is a sentence in a book or a story. And in this case, your reader may not recognize that a capital letter V means voltage. And so it would be a good idea to spell out the word volt for the reader. And if you're going to do that, you should also spell out the number 9. So in this case, option F is your best choice. Number 2 is a question on a worksheet. This could be a worksheet in a science classroom, like you would have in this class. In this case, your teacher will understand that a capital letter V means voltage. And so using that correct symbol is totally fine and would be the best option. The options that I listed as being incorrect are not equally incorrect. I would say the options A and B are particularly egregious, as it appears that the author made no attempt to include the proper unit, and those are especially bad. Let's now look at some examples of displaying units in practice. Here is a figure that includes 3 charts. All 3 of them have the same horizontal axis, which is time measured in milliseconds. Each 3 of these charts has a different vertical axis, which includes its own label and units. You can see that the top chart is measured in millivolts, and the bottom 2 are measured in nanoamps. Here's an example of units in a data table. Here, the units are listed in parentheses after the variable in the header row. The header row has been formatted to be bold and is underlined. The variables are italics, but the units are not. The first column is mass measured in grams. The second column is mass converted into kilograms. The third column is the weight measured in newtons. And the fourth column is displacement measured in centimeters. Here are examples of units in a spreadsheet. Option 1 uses 3 columns. The first column is the variable, the second column is the value, and the third column are the units. Option 2 uses 2 columns. The first column is the variable name and the units written in parentheses, where the second column is the value. Option 3 also uses 2 columns, where the first column is just the variable name, and the second column is the value that has been formatted with a custom format to display the units. Option 1 and Option 2 are the most common options or formats that you will see in spreadsheets. That concludes today's lesson on units and dimensions. But first, before we leave, let's go ahead and review today's key lessons. We saw dimensions and units. We found that dimensions are classifications of different types of quantities, and units are specific ways in which we measure those. For example, length is a dimension, but centimeters, inches, meters, and miles are all units of length. Then we looked at, in great detail, the International System of Units, or SI for short. It is composed of 7 basis units that are defined based on exact physical constants. There are prefixes that scale units by powers of 10. There are 22 derived units that are created by multiplying powers of basis units. And there are specific rules about how to display units. We also looked at unit conversions. Unit conversions are found by finding the equivalence relationship between the target unit and the source unit. Then, with that, we get a form of unity that can be used to multiply with a given quantity to change its units. And then we looked at in great detail how to display units. Basically, units go everywhere. They go on charts and plots, on tables and spreadsheets, in writing, in speech, and even in computations. Here in Appendix 1, let me go through the answers for the correct or incorrect unit expressions. We'll go over these row by row. The green ones are correct. The red ones with a slash through are incorrect. So in the first row, the first two are correct, so there's nothing wrong with them. In the third one, 11 square meter, you need to use a superscript when you square a meter. And that's the only one that's incorrect in the first row. In the second row, they're all incorrect. 8.2, you need a space and then kilogram. In the second one, 8.5, you need a space. And then a capital S is a derived SI unit, which is okay if that's what you mean. If you meant second, then you need to use a lowercase letter s. And the third one, it's hyphenated, which is incorrect. And the fourth one, 3.7 meters per second, you need to use a superscript on the second. And then on the fifth one, you need a space, 3.3 space, and then V. In the third row, kilograms is not plural, you need to drop the S. In the second one, you need a hyphen, and you should not write in italics. Negative 15 amps is correct. 1.3 amps, you need to drop the S. And the last one, do not write in italics. In the next row, 16.77 micro or micron. Micron is a deprecated unit. You need to write micrometer. So put the micro symbol and then use M for meter. The next one, 60 megagrams. That's an unusual unit, but it is correct. And the third one, 8.7 molar. If you mean molar, that's fine. That's an incredibly high concentration. If that's what you mean, then that's okay. If you meant meter, you should use a lowercase letter m. And the next one, mole, is written in italics, which is incorrect. And in the last one, 180 degrees, you should not have a space between the 180 and the degree sign. In the next row, 22 millifarad, you cannot have a compound prefix. In the second column, 1.65 millimole, you either need to write out milli if you're going to write out mole, or you need to drop the E, because the symbol for mole is MOL, not MOLE. And then in the last column, 44 degrees Celsius, you need a space between the 44 and the degree sign, and you do not need a space between the degree sign and the C. And the next row, 98.63 Fahrenheit, you need a space. And the next row, 15.3, there's no reason to have an underscore there, so remove that. In the next column, 140 Newton meter, you need a space, and then you need a space between the Newton and the meter, or a dot. In the third column, 8.5 kilogram per second squared, you need to make the squared superscript. And then in the last column, you need to make the -1 superscripted as well. In the last row, 44 megamolar, which is an incredibly high concentration. If that's what you mean, then that's okay, but you need a space. If you meant millimeter, then you need to have a space, and you need to make those two M's lowercase. In the second column, 300 degree Kelvin. Kelvin does not use a degree sign, so remove the degree sign. And then the next three are correct. Although I will say in the fourth one, 6.14 meter per meter, it's kind of obnoxious. If you meant radians, you would just say radian or put nothing at all. On this slide, I have gone ahead and corrected the formatting on all of the ones that I mentioned were incorrect.